all my viewers, feel most welcome into our today's discussion, whereby we are going to discuss about a kind of repeated roots inverse Laplace transform. This is one of the easiest inverse Laplace transform once you know how to go about the partial fraction. Let us now get into our working by using partial fraction in finding the inverse Laplace transform of this function. We understand that the inverse Laplace transform of 3s squared, we add to 16s, we add to 15, all over s, we add to 3 cubed is equals to the inverse Laplace transform of a all over s. We add to 3. We come and add to b all over s. We add to 3. But now squared, we come and add to c all over s. We add to 3 raised to a power of 3. Those are the partial fractions that we are going to have. Let us now, from this point now, let us now get the value of a, b, and c. For us to have the values of a, b, and c, we are going to have, using the partial fraction, we are going to have 3s squared, we add to 16s, we add to 15 all over s, we add to 3 cube is going to be equals to a all over s. We add to 3. We come and add to b all over s. We add to 3 squared. We come and c all over s. We add to 3 now raised to a power of 3. We are going to take whatever we are having on our denominator here. We multiply by each and every function on the left hand side and the right hand side. When you take whatever we are having here on our denominator, we multiply by this function. We are going to have s, we add to 3 raised to a power of 3. These two are going to cancel out, and on this side we are going to have s, we add to 3 raised to a power of 3. Here we are going to have s, we add to 3, and here we are going to have s, we add to 3 raised to a power of 3. These two are going to cancel out to mean that on the left hand side we are going to have 3s squared, we add to 16s, we add to 15 is equals to, on our right hand side we'll find that here we are having s plus 3, we multiply by s plus 3, we multiply by s plus 3, to mean that here when you come to our denominator here, it is going to cancel out one of the cubed, one of s, we add to 3 function in the bracket, to mean that we are going to be left by a all of a into s, we add to 3 squared, since one of them is going to be cancelled from this point. Here we are going to have, we add to b. On our denominator we are having s squared, to mean that we are going to have s, we add to 3. These two are going to be cancelled out and we are going to have 1. Here we are going to have the whole of whatever we are having on the denominator is going to cancel out with our function there, and we are going to have c into the bracket. We are going to have 1. We can now open the bracket here and get the value of a, b, and c. 3s squared we add to 16s we add to 15 is equals to, we are going to have a into s squared. S is going to be, it's like we are having these two. We are going to have s squared, we come and add to s, we multiply by 3, and then we multiply by 2. We are going to have 6s, and lastly, we are going to have 9, because we are going to square the value of 3. We come and add 2. Here we are going to have b into s, we add to 3, we add to c into 1. When we open the bracket using the value of a, b, and c, we are going to have 3 s squared, we add to 16 s, we add to 15 is equals to as squared, we add to 6as, we add to 9a. We come and add to bs, we add to 3b, and lastly we add to c. From this point now, we need to get the value of a, the value of b, and the value of c. For us to get the value of a, we can come and have our terms of, we can come and select the term of a squared. On our left hand side, we are going to have 3 is equals to a squared we are having here, and it is only at this point, to mean that a is going to be equals to 3. For us to get the term of b, we can either decide to use the constant function or the terms of s. Let us use the term of s to have the value of b. 16, because here we are having 16s, is going to be equals to 6a. At this point, we come and add to, b, because b has got an s. To mean that our value of b, we are going to have 16 is equals to 6 into a was equals to 3. We come and add to b. And here we are going to have 18. When we take 18 to this side, we are going to have 16. We subtract from 18 is equals to b. And our value of b now is going to be equals to a negative of 2. That is our value of b. Let us have the value of c. For us to have the value of c, c has got a constant, and by using the constant, here we are going to take the terms of the constant. To mean we are going to have 15 is equals to, here we are going to have 9a. 9a has, the term of a has got a constant. Here we are going to have, we add to 3b, we add to c. 15 is going to be equals to 9 into, our value of a was equals to 3. We come and add to 3. Our value of b was equals to negative. Here b was equals to negative 2. We come and add to c. To mean that now we can come and have our value of c. Here we are going to have 27. We subtract from 6, we add to c. These two, we are going to have 21, a positive of 21, to mean that the value of c now is going to be equals to, when we take positive 21 to this side, we are going to have a negative of 6 is equals to the value of our value of a. Our value of a was equals to 3. Our value of b was equals to negative 2, and our value of c was equals to negative c. Since I'm not having the space, that is the reason as to why I'm noting them there. We agree that whatever we are having on this side is equals to whatever we are having on the other side. The inverse Laplace transform of a all over s, we add to 3. We come and take b all over s, we add to 3 squared. We come and take c all over s, we add to 3 cubed is going to be equals to, we are going to have the inverse Laplace transform of our value of a was equals to 3 all over s, we add to 3. We come and subtract from our value of b was equals to 2 all over s, we add to 3 squared, and our value of c was a negative of 6 all over s, we add to 3 raised to a power of 3. We are going to take the inverse Laplace transform. The inverse Laplace transform we distribute to each and every term, and by doing that we are going to have 3. The inverse Laplace transform of 1 all over s, we add to 3. We come and subtract from 2 the inverse Laplace transform of 1 all over s, we add to 3 squared. We come and subtract from the inverse Laplace, 6 the inverse Laplace transform of 1 all over s, we add to 3. Everything raised now to a power of 3. We agree that here exponential, the Laplace transform of exponential positive or negative of a t is equals to 1 all over s negative or positive of a. When you check our numerator here, you will find that it is 1. That is the reason as to why I'm factoring out 3, 2, and 1 on the numerator, so that it can matches our function here. We are moving now from the inverse function back to its original function. This one matches whatever we are having here. But when you check at these two, they do not match this kind of a criteria. To mean that we are going to check on the first shift theorem. And when you check on the first shift theorem, the Laplace transform of exponential positive or negative at, when you multiply by our function of t, when you get the Laplace transform of this function, we are going to have is equals to the Laplace transform of t alone. Its Laplace transform is equals to 1 all over s squared. But when we are using the first shift theorem to get its Laplace transform, it means that the term of s must be shifted, to mean that we are going to have 1 all over this term of s must be shifted. We are going to have s negative or positive of a. This was equals to the term of s, but since it was shifted, we must shift it and retain the square. How about now when it is cubed? We understand that t squared is going to be equals to 1 all over s to the power of 3. When we are using the first shift theorem, we understand that exponential positive or negative at is going to be equals to 1 all over. The term of s must be shifted here using the first shift theorem, and we are going to have s negative positive or positive of a, but the term of s was raised to a power of 3. And that is how you go about functions like this one. Once you are good with the first principle of Laplace transform, getting all these functions now will be a kind of very easy. Let us now have our answer, and here we are going to have 3 exponential. We say that when we are having here positive, here we are going to have a negative. And when we are having here a positive, here we are going to take a negative of a. Here we are having a positive of 3 to mean that the coefficient of t, we are going to have a negative of 3t. We come and subtract from 2. Here we agree that we are going to use our function here to mean that we are going to have the exponential. It was shifted with respect to a negative of 3t. And lastly, we subtract from 6 exponential negative 3t negative 3t, and our term of t must be squared. T must be squared. And this is how you go about finding the inverse Laplace transform of our function here. It is just quite as easy as that. Thank you for your time. Let us meet in my next session, whereby I will be still discussing on the inverse Laplace transform. Different examples so as to have a better understanding on inverse Laplace transform before we get into ordinary differential equation using the inverse Laplace transform, which are also very easy to understand. Thank you for your time.